So, Daniel, how did you get into your field? It's an exciting field. Did you
Yeah.
see it coming?
So actually, when I started to study, I studied physics, and I was really interested in physics and astrophysics in general. And back then, when I started, it was not so long ago, but I started to study at the university around '95, and that was the time when the first exoplanets have been discovered. But it was still a very exotic and very small field too. There were very few people who have been working on exoplanets, and actually it didn't get me excited right away. And but as more and more planets have been discovered and we understood how different those worlds are from ours, I think it became apparent for everyone that this is something really exciting. And so when when I had an opportunity to study about exoplanets and start to work on that field, I actually jumped on the opportunity.
So, just remind us, everyone, why people were so surprised. I mean, the discovery had been anticipated for decades. It was incredibly hard to do it, and then suddenly it's like we don't know anything.
That's right. So people have been fascinated with exoplanets, obviously, for a very long time, starting from the Greek, who have been thinking about whether or not there are planets like ours in the universe. Uh, but it's very difficult to find these objects, especially if we take the solar system as a template, which is what astronomers have done, and that's for the reason that that was the only system that we have known. Planets like Earth are very difficult to detect, and in fact, it's only becoming now possible to detect Earth-like planets in larger numbers. There were many attempts to detect planets in the past century, and there were claims actually going back to the 1960s of extrasolar planets around other stars. Um, Most of the claims until 1995 turned out to be false. These were all techniques where people have been not detecting the planets directly, but they have been observing the star and deducing the presence of a planet around the star by for example, the motion of the star, precisely measuring the motion of the star and deducing that there may be an unseen body that moves the star around. So most of these detections, because they are looking for very small signals, turn out to be wrong. And for several decades, this was a field that was so challenging that very few astronomers have tried.
In fact, maybe you can even go further, because I know some of the people and their stories, and it was perhaps a dangerous field for a young person to go into, because there were the graveyard of reputations from false claims and so on.
That's exactly right. Yeah, I think it was, and it was it was very difficult to even get to the precision where you could expect to see planets, and it was very difficult to verify that what you found was really a planet, and basically as many claims turned out to be false. And of course each of those claims have always been reported in the media very broadly because of the excitement that they caused. Any failure was a catastrophic failure very frequently.
Mm-hmm. And then, of course, what gets discovered, this crazy Jupiter-like planet on a 4.5-day orbit. I mean, it's insane. It's closer than Mercury, whipping around a star. So the first one is a huge surprise.
That's right. So that's actually the field. There were competing groups that were trying to find extrasolar planets, and most groups have used the solar system as a template, so they did not expect any planets really close to the host stars. And in fact, in some cases, the rumor says that such planets have been seen, but they were discarded as an artifact in the data because astronomers couldn't really believe that they could be real objects. But one of the groups, that's the Swiss group led by Michel Mayor, actually took the data on face value, and they realized in one particular star in the Pegasus constellation that the star, when you measure accurately its velocity, it seems to change on a 4.5-day period. So every 4.5 days, it basically describes a small circle that you see. And
there's an interesting cultural aside on that, because, as I understand it, there their research field was close binaries, so they were familiar from their own research for the cadence of observation that would let them find a hot Jupiter.
That's right. Basically, they used a technique that was developed to find close stellar binaries, stars that are orbiting each other, and basically just measuring the velocity of one star and recognizing that it's regularly changing as it's moving around its orbit is the same technique then that they applied for finding planets as they got better and better in it. And that's true for many of the techniques that we are now using for finding planets. Many of these techniques have been in the past used to study stars and various stellar companions.
And as the numbers gradually, I mean, the excitement was incredible in the field, and as the numbers of planets found increased, did they make more sense or not? The properties of the exoplanets.
So I think exoplanets are really incredible in a way because they really defy our initial imagination, and they really have turned out to be so much more diverse than anybody could have, I think, predicted. That keeps the field very exciting. We find exotic planets basically every week now, and almost every single property you can think about a planet, we have seen huge variations in it. And so the first surprise were the hot Jupiter type planets. These are gas giant planets, often even more massive than Jupiter in our solar system, that are orbiting very, very, very close to their host stars. In fact, so hot that the day side, the side of the planet that is illuminated by the sun, is almost as hot as a cool star. So that's one of the examples, but we have seen so many other examples for really exotic properties, both in temperature, density, masses, planets orbiting binary stars, really huge planets very far out, or very small planets very close in. Planets that are locked in a resonance. These are planetary systems where the inner one can go around 2 times exactly on its orbit, while the outer one goes around only 1 time. And these are very interesting systems from planetary dynamics.
And I guess one of the theoretical ideas that emerged as these discoveries were being made were that planetary systems are a little chaotic. I mean, they're not quite as regular, and our solar system seems quite quiet and calm.
Yeah, well, we can be fair. So the solar system is really boring. I think that's basically what's emerging from these systems. We have seen really systems that must have underwent much more movement and rearrangements in terms of their orbits than the solar system. Basically, we have very good models for planet formation now, and we can predict and expect where certain types of planets form in a solar system, and we would not expect very massive planets forming very close in. We know that every system that we see where there is a Jupiter-like planet or even more massive, very close to its host star, must have started its life way out in the outer parts of the planetary system, and through interactions, sometimes with the material from which it formed, sometimes in interactions with other planets, it's made its way close to the inner planetary system. And these models often show that planetary systems that are not as stable as the solar system, they can undergo sudden instability, where you can think about almost the planetary system exploding as the planets kick out each other from the system.
Now, the theory and the models must have evolved almost as rapidly as the observations, because as I recall, the migration of planets, I mean, these properties were not really predicted in advance of 1995.
That's right. That's right. So the models are now very good in predicting what we have seen already, which are not the true predictions. But really what happened is that we understand reasonably well how the solar system has formed, and the solar system is not one of the really extreme planetary systems, as we are starting to see now. And I think our models are right, but we have underestimated sometimes the extreme range of properties that planetary systems can form in. And if you consider those, then sometimes the assumptions that we made about the formation of the solar system break down. When you have planets so large that they really thoroughly influence the material from which they form, then the formation process can go in a different direction than we envision. So it's very important, and as always in science, to make predictions and then compare that to observations and then revise your model and again verify it with predictions. And that's exactly what's happening with exoplanets, but in an extremely fast pace. Basically, in about 15 years, we went through several of these cycles, and we now believe we have much better models than we had 15 years ago.
And with, you know, nearly a couple of decades of data, has it been possible to find true analogs of our solar system, boring systems?
So it just so happens, if you would look in a large audience in a football game, the first ones that you would spot out, individuals would be the strangest people probably, with the strangest clothes, or the largest persons, those who are standing out of the crowd. And in terms of finding solar system analogs, that's really our goal, to understand how frequent is the solar system in the universe. And we have not reached the point yet that we can find planets as small as the Earth, as far from the Sun as the Earth is around Sun-like stars. But we are getting very, very close. So NASA has launched the first space telescope dedicated to finding exoplanets. And also, you may not know this, but NASA has over 2 dozen space telescopes of various sizes, but only one is really dedicated to exoplanets, and that is the Kepler mission.
And it's quite a modest-sized telescope.
It's actually a very small telescope. By the standards space telescopes go, it's a very small telescope.
And I think Bill Barucki said it's the most boring. You talk about boring solar system. He says the most boring mission. It just takes a picture every 6 minutes for years. It's the same one part of the sky.
That's right. It's basically, you can think about the telescope as a large tube, where one end open, where the light comes in, it hits the mirror on the other side, and all the light. This is a parabolic mirror. It's a curved mirror, and it collects all the light in one single point, the focal point. And there are no real moving parts in this telescope, and the soul of this telescope is what is in the focal plane. What in the focal plane, what you would find is a large array of CCD chips. So these are chips just like the ones you have in your iPhone, but larger in size. And these arrays, there are 42 of those chips, they can continue observing the same roughly 160,000 stars for years, as you said, Chris. Mm-hmm. So otherwise, not much else is happening with the telescope.
And in exoplanet work, it sort of feels like the field divided into before Kepler and after Kepler, because the numbers just went through the roof when Kepler had done a few months' work, say. So describe how did it make such an impact so quickly? So
it's so there are several aspects to it. So I remember the time not so long time ago when there were so few exoplanets that we all knew all the names of exoplanets, right? It was 5, 6, and then half a year later a 7th was discovered, and everybody was excited that the 7th is so different from the 6th, right? And this situation has changed completely when now exoplanets are released often by hundreds. So the current number is, I believe, and I have to check it every day, that we have about 600 to 700 confirmed exoplanets, mm-hmm. and more than 2,300 candidates from Kepler. Kepler has released, the last release was 400 new planet candidates. And
what's that distinction mean? Because it's a lot more candidates than confirmed. Does it mean that they're going to go away, or they're not?
That's a very good point. So Kepler, let me tell you a bit how Kepler works to understand this. So Kepler is staring at these 150,000 stars continuously and looking for what we call transit events. And a transit event is if you imagine a planet orbiting a star, and you imagine just flying around the orbit and moving in a position where the orbit goes in front of the star. So in that situation you would see basically the planet during moving around its orbit passing between you and the star. And when that happens, the planet will cover a small patch a small part of the surface of the star, right? So Kepler is so far away from these stars that it cannot actually resolve these systems. All it sees is the light from the star. But it will see the light dimming slightly when the planet is passing in front. So with this situation, basically Kepler is looking for these faint dips that sometimes they only happen once a year. For example, in the case of Earth, it would happen only once a year exactly because of the 1 year period. So Kepler is looking